Welcome to example number 7. We have a helicopter with its rotors that are rotating. And so we have this blade here, another blade here, another blade here, and we can see that we're given some information about the rotor blades. Let me write that down, I guess. We have given that the length of the blades, L, is 5.2 meters. We're told that each blade has a mass of 160 kilograms. And we are also told later on in the problem that it reaches a final angular velocity of 5 revolutions per second, which we probably have to convert to radians per second. So we know that it actually starts from rest, 0, and it does this in a time interval of 8.0 seconds. So what we're asked to find is we want to find in A part the moment inertia of this rotor blade system. And part B, we're asked to find the torque on the system, and that's about it, right? So I think I'd like to show you a little animation to kind of help you visualize it. Well, here you go. I've got basically 3 rotor blades here, and I'm going to press click on the screen in a moment, and it's going to actually show you it accelerating over a 2-second period. There you go. So on the graph, it shows you the angular position over time, and then over here on the second graph is the angular velocity over time. It's in radians per second, which initially I'm given in revolutions per second, but I made this little animation to help you kind of understand what's happening. All right, let's go back to the notes here, or to the example, and let's go ahead and calculate the rotational inertia of the system. So in part A, we're trying to find the rotational inertia of the system. Well, there are basically 3 blades. And so how do you find the rotational inertia of a rod, essentially? If we assume this is a rod, we have to go back to our notes right here where we have these table of rotational inertias that are provided. And of course, these will be given to you on a test. We're rotating the blade from essentially the axis. So it's really using this formula. We're not using this one because we're not rotating it about the center, we're rotating it about the end point. Right? So this is the axis of rotation. So the formula we're going to be using is 1/3 ml squared. All right? And so we're going to be applying that in this equation. So we have 1/3 ml squared. And we have 3 blades, so we multiply this by 3. So that actually just turns out to be nicely just ml squared. So we plug in the mass of 160 kilograms, and then we apply and put in the radius or the length of the bar is 5.2 meters. We square that. We get a rotational inertia when you plug it in to roughly 4,326 kilograms times meter squared. Okay. Moving on to part B, how do we find the torque? Well, we're applying Newton's second law, basically rotationally. So sum of tau equals I alpha. We already know what I is. We just calculated in part A. What we don't know yet is alpha. So we need to calculate alpha. So alpha is the angular acceleration, by the way. So it's the change of angular velocity over the change in time. Final angular velocity minus initial angular velocity over that time interval. Now we got a little bit of a problem here that's in revolutions per second. We got to convert that to radians per second. So let's go ahead and do that. So the initial angular velocity is 0, right? We have 5 revolutions per second, all right, over a time interval of 8 seconds. We got to convert this. We want our alpha to be in radians per second squared. So in order to do this, we need to change revolutions to radians. If you recall, 1 revolution is essentially the same thing as 2 pi radians. So we want to get revolutions gone, so we have radians. So we're going to put revolution on the bottom, 1 revolution, and we know we're going to put 2 pi rads on top, right? We'll see the revolutions cancel out here. And so really what we have is 5 times 2 pi divided by 8. And if you plug that into your calculator, you'll get around 3.93 radians per second squared. So now you got the torque. Calculate. Torque is simply the rotational inertia, 4,326 kilograms times meter squared, multiplied by the angular acceleration of 3.93 radians per second squared. All right, and our net torque, when you multiply these two out, will be 16,990. And when you work out these units of kilograms times meter squared all over second squared, they come out to basically the units of torque, which are newtons times meters. Okay, that's it for this example.